Today we're doing section 5.1, Eigenvectors and Eigenvalues. The basic concepts presented here, eigenvectors and eigenvalues, are useful throughout pure and applied mathematics. Eigenvalues are also used to study difference equations in continuous dynamic systems. They provide critical information in engineering design, and they arise naturally in such fields as physics and chemistry. Let's look at example 1. Let A be this matrix U and V. Examine the images of U and V under multiplication. So down here, we have vector U, vector V, and we're going to look at AU and AV, okay? So AU would be 0, -4, -2, 2, times 1, 1. And when we multiply that, we get -2, -2, which also we could factor out that -2, which would then just be -2u. So here, if we look at that, this would be AU. Okay, let's look at AV. This is multiplied by -1, 1. And when I multiply that out, I get -2, 6. With this one, we could factor out a -2, but we would be left with 1, -3, which is not anything. So this would be AV up here. So with this, U is called an eigenvector of A. Because AU is a multiple of U. And then V is not an eigenvector of A. Since AV is not a multiple of V. An eigenvector of an n by n matrix A is a non-zero vector x such that A times x equals lambda x for some scalar lambda. A scalar lambda is called an eigenvalue of A if there is a non-trivial solution x of A of x equals lambda x, such that the vector x is called an eigenvector corresponding to lambda. Our vector x cannot be the zero vector. Let's look at example 2. Show that 4 is an eigenvalue of A and find the corresponding eigenvectors. Okay, to show that 4 is an eigenvalue of A, we need to show that 4 is a multiple of that. Okay, so go ahead and doing that. We first need to set up AX equals 4x. So then with this, in order to solve this, and we would have to set it equal to 0. So I'd have AX minus 4x equals 0. And then whatever one we're trying to find is the eigenvalue, we need to multiply that by I, our identity matrix. So here, I would have A minus 4I times x equals 0. So here, to show this, I need to find a minus 4i. And that shows that 4 is an eigenvalue of that. So my a minus 4i would be 0, negative 4, negative 2, 2, minus 4i would be 4, 0, 0, 4. This would give me negative 4, negative 4, negative 2, negative 2, which is a minus 4i. Now we need to find the corresponding eigenvalues, eigenvectors for this. So in order to do that, we need to solve a minus 4i times x equals 0 using an augmented matrix. So we need to solve negative 4, negative 4, negative 2, negative 2, this. And we're going to use an augmented matrix to do that. And what I can do is I can take negative row 1 and add it to row 2 to get all zeros in row 2, and negative 1/4 times row 1 to solve it. So I'd have 1, 1/2, 0, and 0, 0, 0. So here I have x1 equals negative 1/2 x2, and then x2 is free. Now I need to take x1 plus 1/2 x2 equals 0 and go ahead and write that as a vector equation and solve it. So I would have my x would actually equal negative 1/2 x2 plus x2, which I could then write that as negative 1/2 x2, which would then be x2 times negative 1/2, 1. So each vector in the form x2 times negative 1/2, 1 is an eigenvector corresponding to the eigenvalue lambda equals 4. So this 4 here is my eigenvalue. So this is my 4, my eigenvalue. And every vector in this form is an eigenvector corresponding to the eigenvalue lambda equals 4. So if I look here, I have my v, if we were to call this v, and this would be AV, which would be 4b, if we were to call that v. Just as a little warning, the method just used to find eigenvectors cannot be used to find eigenvalues. The set of all solutions A minus lambda I, x equals 0 is called the eigenspace of A corresponding to lambda. Let's look at example 3. Let A be that matrix. An eigenvalue of A is lambda equals 2. Find the basis for the corresponding eigenspace. So with this, since we know lambda equals 2, we know that AX equals 2 times X. So we're first going to find A minus 2i. So then we would know from our previous example, we'd have A minus 2i, X equals 0. And we need to go ahead and solve that. And yes, you do need to show work. So here's A minus 2i. And that would give me 0, 0, 0, negative 1, 1, 1, negative 1, 1, 1. Next, we need our augmented matrix and we need to solve. So now we need to solve A minus 2i x equals 0. And when I do that, I can take row 1 plus negative row 2 to get 1, negative 1, negative 1, 0. I can take row 2 plus negative row 3 to get 0, 0, 0, 0. And I can take row 3 plus negative row 2 to also get zeros here. So x with my x1, x2, x3 would be x2 plus x3. This would just be x2 because it's free, and this would be x3 because that's also free. So this would be x2 times 1, 1, 0 plus x3 times 1, 0, 1. So the basis for the eigenspace corresponding to lambda equals 2 is 1, 1, 0 and 1, 0, 1. And here, if you were to look at that, this is the effects of multiplying vectors and eigenspaces for lambda equals 2 by a. So this would be, for example, if I had v, u, w, this would be a, v, a, u, a, w, and that's what would happen to it. Let's look at example 4. Suppose lambda is an eigenvalue of a. Determine the eigenspace for a squared and a3. In general, what is the eigenvalue of an? Okay, so since lambda is an eigenvalue of a, there is a non-zero vector x such that ax equals lambda x. So if I wanted to show a squared, I would multiply both sides by a. So I'd have a times ax equals a times lambda x. Now I can go ahead and rewrite the right side. So I leave the left side how it is, and I would rewrite the right side lambda times ax. Well, we know that ax equals lambda x from up here. So ax equals lambda x. I can replace this ax with lambda x. So I would have a times ax equals lambda times lambda x. Therefore, a squared x equals lambda squared x. So therefore, lambda squared is an eigenvalue of a squared. So we could go ahead and do the same thing. Here we'd have a times a squared x equals a times lambda squared x. This side we would have a cubed x equals lambda squared times ax. And from the beginning, ax equals lambda x, so this ax can be replaced with lambda x. So I have a cubed times x equals lambda squared times lambda x. And then I have a cubed x equals lambda cubed x. So therefore, a cubed is an eigenvalue of, or lambda cubed is an eigenvalue of a cubed. So in general, lambda n is an eigenvalue of an. So theorem 1. The eigenvalues of a triangular matrix are the entries on its main diagonal. Proof for the 3 by 3 upper triangular case. So when I have matrix A here, x has to be not equal to 0 in order to be an eigenvector. So then I have a minus lambda I times x equals 0. If vector x is not equal to 0, then it has a non-trivial solution. So when I have a minus lambda I, here I have my upper triangular matrix minus lambda I, we would have all of these minus lambda. By definition, lambda is an eigenvalue of a if and only if a minus lambda I x equals 0 has a non-trivial solution. This occurs if and only if a minus lambda I times x equals 0 has a free variable. Theorem 2, if vector vi to vr are eigenvectors that correspond to distinct eigenvalues lambda to lambda r of an n by n matrix A, then vector v1 to vr is a linearly independent set.